So if we continue on with this idea and we look at a way to calculate the energy changes in a given atom. So we're focusing on the hydrogen atom, right? Because frankly, the Bohr model is really only useful to study the hydrogen atoms. And this is one of the major reasons why we'll see a shift away from the Bohr model as we get closer and closer to ultimately the quantum mechanical model of the atom. So we see that the wavelengths in the emission spectrum can be predicted by calculating the difference in energy of the two states. Now, the energy of the photon is exactly equal to whatever that energy difference is. Now, we used an equation earlier to predict the wavelength. Now, we can sort of alter that equation a little bit to give us an equation that will directly give us the energy gap between the two levels that we're interested in. So we have the energy difference between the atom is going to be equal to this constant, this is called the Rydberg constant, times, again, 1 over n final squared minus 1 over n initial squared. Now, again, we need to understand that the energy of the photon, so this should not be change in energy, sorry, this should just be the energy of the photon is going to be equal to this change in the energy of the atom. Now, notice there is a sign here, right? And then you'll notice is that all the energy changes in the atoms are negative, right? That's simply because, right, they're falling in energy. But the energy of the photon is, of course, always a positive value, right? The photon doesn't have negative energy, so your energy changes of atoms are going to be negative values, but your energy of the photon is always going to be a positive value. So if I want to take that same gap that we looked at from 6 to 2 and calculate the energy of the photon that's released when we see this relaxation, I simply plug it into this equation, right? So the energy change of the atom is equal to negative 2.18 times 10 to the negative 18 joules times 1 over 2 squared minus 1 over 6 squared. And if we do all this math, we get, there, let's switch to black here, a little easier to see, minus 2.18 times 10 to the minus 18 joules times, that's 0.222. Again, do the math. We get 4.84 times 10 to the minus 19 joules is the energy change within the atom. That means the energy of the photon is going to be 4.84 times 10 to the minus 19 joules. Now, not surprising, if we use our equation, energy of the photon equals hc over lambda, we would come up with a wavelength that is approximately equal to 410 nanometers, just like we saw a couple slides ago. So whether you calculate the energy of the photon, right, based on the energy gap between the levels that we're dealing with, right, we can get that energy of the photon. That allows us to calculate the wavelength of that energy, and we can associate that with some line in the spectrum. Hi. One of the most important aspects or discoveries or proposals associated with quantum mechanics came in 1924 when de Broglie proposed that, similar to waves, that electrons could also behave not only just like particles, but like waves. So, in other words, that these very tiny particles, like electrons, could have the same kind of dual nature that had been explained for electromagnetic radiation. So de Broglie proposed the wave-like nature of electrons in 1924, and he gave the following equation for the wavelength of a particle. Now, in this case, the wavelength of a particle is equal to, again, that constant, Planck's constant, divided by the mass of the particle times the velocity of the particle, or the mass times the velocity. So, for example, if we wanted to calculate the wavelength of an electron, we would need to know how fast it was traveling, and we would need to know its mass. Now, of course, the mass of an electron has been established, and we could measure how fast that electron was traveling. So if I were to set up this calculation, the wavelength of this electron is going to be equal to, again, Planck's constant, which is 6.626 times 10 to the negative 34th joules seconds, divided by the mass, 9.11 times 10 to the negative 31 kilograms, times the velocity of this particular electron, 2.65 times 10 to the 6th meters per second. Now, units here can be a little bit confusing. So it doesn't look like things cancel out. But what we need to remember, and we saw this a little bit ago, is that a joule, right, the unit of energy of a joule, is actually equal to kilogram meter squared per second squared. So if we think about it in that way, the joule here, right, the kilograms of those joules will cancel out to the kilograms here. The meters, one of the meters, right, will cancel out to the meter down here, the division of meters. The seconds will cancel out with one here and one here. And the only unit we're left with is meters, which would be the expected unit for wavelength, right? So the wavelength of this electron is going to be equal to 2.74 times 10 to the minus 10th meters. So what de Broglie proposed, and was later confirmed by experiment a few years later, was that electrons not only have these particle-like properties, mass, etc., but they have wave-like properties, wavelength, right? And so this dual nature of electron, in very much the same way as electromagnetic radiation, has a dual properties, has that wave-particle duality. Now, just as we saw with electromagnetic radiation, one of the best ways to see the wave-like properties is through diffraction. So while I did not put the pictures in the slideshow, if you look in the book, and there's a video that is going to be on Talon right after this lecture slide, demonstrates what is observed when you do a diffraction experiment with a beam of electrons. But to sort of cut to the chase, what you should notice is that when you conducted that famous two-slit experiment with a beam of electrons, that you see an interference pattern, right? And this was used as proof that the electron does have a dual nature, does have that wave nature, because the only way that you could see that classic two-slit wave interference pattern is if the electron was behaving as a wave. Otherwise, if it was behaving only as a particle, you would just see two bright spots right after the slits, because of course particles don't diffract. They would just pass right through the slits and go straight on to give you two lines to line up with the slits, not the interference pattern which is observed. So at this point, right, we've established the dual nature of an electron, that it has both particle and wave type properties. Now, one of the last pieces leading up to sort of the culmination, another building block to this whole quantum mechanics idea, is what's known as the Heisenberg uncertainty principle. Now, this was proposed by Werner Heisenberg in 1927, and what he stated was that the uncertainties in both the position, which might be considered a particle property, and the velocity, or sometimes this is referred to as momentum, right? A lot of times we just think about this generically as the pathway that it's traveling, right? Where this would be associated with the wave nature of the electron is that the uncertainties in these two properties, where exactly the electron is and how it's moving, are inversely proportional to its mass. Right? So Heisenberg stated that the product, so if you take the uncertainty in the position and the uncertainty in the velocity of the particle, you multiply those two things together, you get an inverse proportionality to its mass. So in other words, the greater the uncertainties, so as particles get smaller and smaller, right, the uncertainties get bigger and bigger. Now, what he also stated was that the more accurately you know one of these things, the less accurately you know the other. So, for example, if you know the position very well, then you're not going to know the speed or the velocity very well. You're going to lose information, and vice versa. And so he came up with this uncertainty equation that says that the uncertainty in the position times the mass times the velocity, or the momentum here, has to be greater than or equal to this constant, which is Planck's constant over 4 pi, greater than or equal to. So in order for this to be true, right, as one of these goes up, the other one has to go down, or as one of these goes down or becomes more certain, the other one has to become less certain. And so these two things are known as complementary properties, right? The position and the velocity of an electron or a small particle are complementary to each other. The more you know about one, the less we can know about the other. And so what ultimately comes of this is that the best that we can do is describe a probability of the electron position in a particular region of space using statistical functions. So again, since we can't be totally certain about both of these, we can't know both where it is and where it's going, if you will, the best we can do is, based on what we know about the electron, is we can come up with a probability map of where that electron will be found in space, or in other words, around the nucleus. And so this idea of de Broglie, of the wave nature of an electron, and the uncertainty ideas that Heisenberg gave us ultimately lead to the development of quantum mechanics by Schrödinger, with contributions from a lot of these other people.